Hello everyone. In this video we are going to look at the Unscented Kalman Filter, or UKF, which is an alternative to the Kalman filter when the system is nonlinear, when the equations for observation and for the state transition are nonlinear, and a better alternative to EKF when these equations are highly nonlinear. So the system the states of the system jump around, they act kind of like chaotic, like complicated data series and so on. EKF is not going to do an amazing job in such cases, and so that's where the UKF comes into action. So what does this UKF do? So first, let's look at what does EKF do, so then we can go to UKF. What EKF does is, if we go back and look at my lecture that I had on the Kalman filter, you see that the state and the uncertainty, the covariance matrix, they were transformed from the prior knowledge from the previous state to the next one through these matrices, right? A and specifically C. These are the things, especially A for state transition is the one that later you see. Here, look, I'm transferring the previous mu to the new mu through A and B, and I'm also using what? Using my C matrix into the update states, the correction state, right? You see, so it's a linear transformation from a Gaussian probability of initial belief to the next belief to the next to the next. And because these relations are linear, therefore these future probabilities of the next state and the next and the next, these are all going to be Gaussian as well. And all we need is just a linear transformation. Now, when EKF is used, we don't have these linear relations, okay? We have these functions f and g, but what we do is to stick to the method of Kalman filter and use the same transformation. We locally linearize these functions f and h using their Jacobians, capital F and capital H. And so basically we use what? We use the exact same formulas that we had for Kalman filter for both prediction and correction. So we basically break down the nonlinear function into small patches of linear behaviors, and then for each one of those linear patches, small patches, we use what? We use a linear transformation of Gaussian. And we learned that under such cases, the extended Kalman filter is not going to be perfectly optimal, and this K gain is, we call it the near optimal Kalman gain, okay? And still works if the system is nearly linear, okay? Or if those nonlinearities in F and H are not really bad. So what if they are really bad? What if that linear approximation is not a good idea? So the UKF is using a transformation called unscented transformation, or UT, where it got its name, UKF. And what does this one do? So instead of propagating those Gaussian distributions through those first order approximations that EKF does through those Jacobians, UKF does what? It uses a sampling technique, which we call the unscented transformation, okay? And by that sampling technique, it handles the nonlinear parents directly. How? How does it do that? It picks, and I'm going to go through mathematics, but it picks a bunch of sample points, which we'll later call sigma points, around the mean of the prior information. Then it passes those sigma points through those nonlinear functions f and g, which could be arbitrarily highly nonlinear, And then it gets what? It gets these new transform data from which it can find a new mean and a new what? Covariance. So it does not apply a simple linear transformation on the mean and on the covariance matrix. Rather, it calculates those through what? Through this sampling techniques. So if you remember in EKF, one more time, if the average of the prior information is M and the covariance matrix of them is capital M, you can show it with mu and sigma, doesn't matter. And if the linear transformation is shown by T, in the case of EKF, that T could be what? Capital F or capital H, then the posterior, the mean of the posterior is going to be T times M, and the covariance of that is going to be TMT transpose, right? Where again, T could be what? That capital F that you had in EKF. But this method does it differently. So what does it do? It says, well, let's say that my my prior information is Gaussian, okay? First of all, there is no guarantee that when I pass this Gaussian distribution through this nonlinear function, the resulting distribution is still what? Still Gaussian. It's not the case. Now, to show that to you, here I wrote this simple code in MATLAB. Here I have a normal distribution, a multivariate normal distribution, and I generate 1,000 random numbers from that, where the mu for it is 0 and 0, so it's a 2D random normal distribution, and the sigma is 1, 0, 0, 1. I generate 1,000 numbers, and then I plot it for you, which you should expect basically a circular distribution in this case, right? If you look at it from the top, then I pass those x and y from the Cartesian normal distribution Z1. I pass them to the Cartesian to polar conversion functions, where r is what? X squared plus y squared, and here you can use a half here, 0.5, right? And then theta is what? Arctangent of y and x, and I use arctangent 2 so that I can get what? I can get quadrant corrected angles. So now r and theta are the transform version of x and y came from a 2D normal distribution. Now the question is, would r and theta also show themselves as a normal or Gaussian distribution? So let's go ahead and look at the results, and you clearly can see that's not the case. While here you clearly can see this elliptic behavior here, right? Let me add some ellipse here, right? Well, you can clearly see that ellipse here, yes? You cannot necessarily see that over here. Here is kind of more like a rectangle. As you can see on these corners, that here and here and here and here, you don't have too much data. Here you do. So kind of here is like a box, if I say, if it's a rectangle. So you see that the distribution in r theta is more of a rectangle rather than an ellipse. And clearly here, a simple transformation of mu and sigma to this one is not necessarily correct. So what does this method do, this unscented transformation? It comes and, as I said, it picks a bunch of points called sigma points around the mean of what? Around the mean of the initial distribution, which could be Gaussian, and then pass these sigma points to the through the nonlinear function, and it gets what? It gets these transform sigma points. And then basically from these transform sigma points, it finds a mean for the transform data, and it finds what? A covariance for the transform data. So this one is not equal to the partial of this g, right? The partial of this g with respect to x times what? Times the original average m. This is clearly not equal to that, and this covariance also is not equal to what? To that partial of g with respect to x times the original covariance, which we showed with capital M, or we can show with sigma, times what? Times partial of g with respect to x transpose. It's not that similarity transform here. Okay, it calculates them for you through simple mean and basically covariance formulations, and I show you in an example. I show you a numerical example in a second. But this is how this unscented transform is working, and so it does not really care how difficult, how highly nonlinear this function g is. As long as you have sufficient number of sigma points, you should be able to calculate these two new entities that you need for Kalman filter formulation. One thing I need to mention is the name unscented is not really referring to anything special. The unscented transformation creator, Jeffrey Ullman, said that he picked this name to really not referring to anything because his name also starts with letter U. He did not want this filter to be called the Ullman filter, so he picked some arbitrary random name apparently for it, and he called it what? He called it the unscented filter, just if you're curious where the name comes from. Okay. So Ullman in his dissertation showed that, as I just showed you here in the simple example, that just having a mu and a sigma is not enough to define what? The transformation. He showed that these two formulas I showed you, this similarity and this one, they only hold for the first moment, which is the mean, and they only hold for the second moment, which is the covariance. And if you go up in the moments, right, if you look at the skewness, kurtosis, and higher moments, for those, these transformations are not going to work. And that's why, in general, this idea of linear or linearized transformation of mu and sigma are not a good idea. In general, you can have infinite number of possibilities of underlying distributions that share the same mu and the same sigma. Okay? Now, how many points should we pick for sigma points, and where are they? Where do we pick them? He showed that if the dimension of your space is n, if you're working in n dimensions, let's say you're working in a two-dimension state space, for instance, you have a second order differential equation which has two states, x and x dot, let's say, then you need n plus 1 sigma points, and not only it's necessary, it's sufficient to define what? A discrete distribution having a mean and covariance. So if you're working in two-dimension, all you need is 3 sigma points, okay? Now, which 3 sigma points? So Ullman, for 2D space, suggested these 3 sigma points if the original distribution has a mean of 0 and a variance of 1. He suggested these 3 points. 0 and 2 transform over 1 square root 2, square root 3 and 1 over negative 1 square root 2, and negative square root 3 and 1, and 1 over square root 2 with a negative sign. And you can show that these are the vertices of an equilateral triangle centered at origin, right? So if I draw this original distribution, which has this mu of 0 and a sigma of 1, right? So basically it looks like this one here, right? Then the points are where you have 0 and 2 over square root 2, so it's 2 square root 2 or 1.4. So the first point is like here. The next point is square root 3 over square root 2 and 1 over square root 2, both negative. So it comes basically like there. And this one, you see the x of it is positive, the y of it is negative, so it comes there. So these are what? The corners of the equilateral triangle around the origin. And in general, if you have more dimensions, if your state space has more dimensions, I'll show you a formula, okay, or several alternatives that you can pick these sigma points. But first, to understand this unscented transformation, let's look at what? Let's look at some numerical example to better understand it. And before we do that, one extra thing we need to pay attention. Here, he was focusing on a average of 0 and variance of 1. What if the average of the original data is not 0 and their variance is not 1? Then he said that what you need to do is the desired sigma points that you have here, you should what? You should basically multiply them by this matrix square root of the sigma, that in this case is not 1 and 1, and then add that mu, which is not equal to 0, right? So this mu is not equal to vector 0, and this sigma is not equal to the identity matrix. Okay, in this case, we can multiply these 3 points by square root of the matrix square root of sigma. What is it? I'll show you, and then adding mu to it before applying this nonlinear what? Transformation. So let's look at a numerical example. Let's say here we have a Gaussian distribution for which the center is at 12.3 and 7.6, and the covariance matrix for it is not identity, rather it's a diagonal where diagonals are 1.44 and 2.89. Which sigma points do we pick for this distribution? And then the nonlinear functions that you need to pass the data from this original Gaussian into are the Cartesian to polar conversion function. So r is the square root of x squared plus y squared. Theta is arctangent of y over x. So first thing is, we have these 3 points, but we are not going to use them directly. First, we need this matrix square root of sigma. What does it mean? Means that you apply the square root on each one of these elements and get m to the 1/2, which is 1.2, 1.7 on diagonal, 0, 0 off diagonal. Okay? Then what? Then you multiply this m 1/2, m to the 1/2, by each and every one of these points, and then add to the result of that what? This average. Okay? So the first point becomes what? The first point becomes that m multiplied by this, which is 0 and square root 2. So first we multiply this by what? Multiply this by 0 and square root 2. And then what? Add this guy to it. Well, what would you get? So if you multiply, the result is what? The result, the first number is 0. If you do, the second number is 1.7 times square root 2. And then add to it what? 12.3 and 7.6. And if you do that, you see the result is going to be what? Is going to be 12.3 and what? 10. So this is your first sigma point. Then you apply the same transformation on S2. If you do that, you're going to get what? 10.8 and 6.4. And if you apply the third one on S3, you're going to get 13.8 and 6.4. So here, if you draw it again, this time your average is what? At 0.123 and 7.6. So it's here, the average, right? The mu is here. And then these points, if I plot them for you, so let's say this is 12.3 and 7.6. If you look at these points, the first one is 12.3 and 10, right? So it comes right here. The next one is 10.8 and 6.4, right? So it comes right here. And the next one is 13.8 and 6.4, which is here. So you still see that these three sigma points are on the corners of equilateral triangle that contains your average. And the size of these triangles depends on what? Depends on these square roots of the covariance. So now these are my what? These are my sigma points. Now what do I do with these sigma points? I pass them to these functions for r and theta. So first I plug in 12.3 and 10 into here. That gives me one number. Then I plug 12.3 and 10 into here. That gives me another number, r and theta. If you do that for the first sigma point, the result is going to be what? This guy here, 15.85 and 0.68. For the second sigma point, this is the projected sigma. And for the third one, you see what? You see that the result is this bottom one, 15.18 and 0.44. Okay, so now I got what? I got my transform sigma points. These are the transform sigma points. Now, how do I get the new average or the average of and the covariance of the transform data? How do I do that? Well, based on what we know from statistics. We simply what? Add these 3 points together and divide by 3. So if you do that, the average of these transform points, the new mu is this, 14.539. And if we subtract each one of these points from their average, square it, and then divide by the 3, the whole summation, your new covariance matrix is going to be this one. Okay, so this is the mu and this is the sigma that you have to use in what? In your prediction stage. Let's go back here. So instead of, look here, you see how I am projecting my covariance matrix? I pre and post multiplied by the Jacobian f here, right? Here, I'm not going to do that. Instead, I'm going to do what? Look. I'm going to pick my sigma points, transform them, and then from those transformed data, I'm going to calculate my this one here, this new covariance matrix. Now, you might wonder if we did do those linear transformations, would we get different results? The answer is yes. If you use the Jacobian of those r and theta functions and multiplied by the previous mean and covariance, this is going to be your new covariance, this is going to be your new mean. And here you might say, well, look, they are not too much different. This here and this one compared to this two, they are very close. You are right. And the sigma, if you look, they are quite close too. Now, sigmas are not as close as the mu's are, but clearly you see that it's not a huge amount of error. The problem is when you are doing object tracking or localization or SLAM or anything like that, these small errors over time will accumulate. And when they accumulate, that is going to cause your EKF to what? To not show such a great performance. And I'm going to show you in an example soon, but it's the accumulation of these small errors that is important. Now, again, if you look, the average of the linear transformation and the average of the UT method are not too different, but if you look at sigma, something interesting is if you look at the sigma done by this UT method, you see that most of the components here are bigger. I mean, compare 2 against 1.92, compare this 0.44 here, not necessarily the diagonal ones, I would say, Kind of, but this one is clearly, this 2 is clearly bigger. And that is one of the problems we had was EKF will underestimate the covariance, and UKF here you see that typically it doesn't. But the averages are very close, and one of the reasons for that is if you look back at your EKF does not use this kind of linear transformation for the average. It does use the linear transformation for the similarity transformation for sigma, but not for the average. Let's go back and look. Here, you see, the new x is not a times the old x plus b times u. They are directly passing the previous x and u to the f function, which is nonlinear, and getting the new x. That's why, since for the mu, the nonlinear function is used, EKF approximation of mu is not really bad. It's this part here is the second formula that is the similarity transform, which is replaced in the UKF by its sigma points. Okay, so what's good about the UKF? We learned. Is there anything else good about UKF? Yes. What is it? UKF clearly does not need to know this Jacobian, so it does not need explicit what? Differentiations. Okay? Because sometimes this f function could be very complex for taking derivatives, or it might be kind of impossible sometimes for taking derivative. I mean, imagine if this f function was not something like square root of x squared plus y squared. It was something like the modulus of x and y, right? Something like that. How would you take derivative of this? Okay? Yeah, now in real physical systems, we don't have really much of modulus or something, but there are functions in mathematics that you might what? You might have a hard time taking derivatives from them or not be able to at all. So the fact that UKF does not need the Jacobians and derivatives is a positive thing. Okay, so this is about sigma point unscented transformation. Now, how is this unscented transformation applies to the Kalman filter? How would you combine it? So in UKF, one way to get the sigma points, here we're going to show them with S0 all the way to Sn. For original data that you have from the Gaussian distribution, which you can show them with x1, x2 all the way to xl, is like this. You select your x0 to be the previous mean. Okay? Then you need two sets of weights, W0A and what? W0C. In general, they are WJA and WJC. There are two types of weights that you need, and the name for them, the WJA, we call them first order weights, and WJCs are called the second order weights. Okay? So there are two types of weights, WJA and WJC, and we need to calculate them, okay? And this J can change. This is the index for the sigma point, okay? So this one does change. You see here, J goes from 1 to 2L. And for 0, when the j is 0, then you can pick them to be equal to each other and any number between -1 to 1. So you can just go ahead and pick them anything that you want. Then what? After j of 0, so from j of 1 to 2L, now again you pick them equal, but here, use this formula, 1 minus W naught over 2L. L here is the number of original data points. And this parameter W naught in general, which is the weight of the mean value W naught, this guy here can be chosen arbitrarily. So you have, this is like a parameter that you can pick. Then what? Then Sj, where j goes from 1 to L, so here are the first set, right? This S from j of 1 to L, this is equal to that previous mean plus what? Plus square root of L over 1 minus W naught times Aj. And then from, if you see here, they are all added with some L. So from L plus 1, literally, so here is from S of L plus 1 all the way to S of 2L. This one is from S of 1 all the way to S of L, and this is S of 0. So from L plus 1 to 2L, again, you pick the prior mean plus the same thing, but this time minus. The only difference is what? This is this minus that square root of L minus W naught times Aj. Now, the previous mean is clear what it is. L is clear. W naught is picked arbitrarily. The only thing is, what is this Aj here? What is Aj? So let's see what the Aj is. So Aj is the jth column of matrix A. Where does matrix A come from? It comes from the Cholesky decomposition of the previous covariance. If you apply a Cholesky decomposition on the previous covariance P of k minus 1 given k minus 1, if you write it as A transpose, which we call a Cholesky decomposition, then you get the A matrix, and this A matrix in general has what? L columns. The jth column of that A matrix, we call it Aj. Okay? Yes? And this method, by the way, we call it the square root unscented Kalman filter, because here this is kind of like this A is like a square root of this P. Okay? And you also have the square root here in the formulas for picking the sigma points. So this is one algorithm for picking up what? For picking up all of these sigma points. Now, how many sigma points do you have? Clearly, as you can see, the number of sigma points, this n is equal to what? 2 times L. So you have a total of 2L plus 1 sigma points that you're going to determine. Okay? Yeah, for Lx's, you get 2L plus 1 sigma points. This is one way to pick up the sigma points. Okay, now I got my S's, fine. Now what do we do? Now that using this xk minus 1 and pk minus 1, right, you could determine the sigma points. Now you pass them through your nonlinear function f, which is for state transition model. Okay, or h, or both of them. So now you pass them through f. F is the same as this g in this picture. Now that these s's are determined, pass them through this f or g in this case and get the transform sigma points. Let's go back. Get the new what? Get the new transform sigma points, and then from them you compute what? The mean and the covariance matrix of this transform sigma points. Okay, so if you pass these sigma points through the f and call the result xj, then you weight these xj's using those waj's, and that will give you the what? The predicted new average. And then using the wcj's and this covariance formula, you get what? You get the new predicted what? Covariance matrix. So this is only what? These two are only the prediction step. And why do we call wja and wjc first order and second order weights? You see that in the application, right? WJAs are the weights of linear terms or first order terms to calculate the average. WJCs are the coefficients of quadratic terms here to calculate what? The covariance. That's why we call them first and second order weights, and the way we calculate them is all what? Using this formula up there. Good? So now our prediction is done through equations what? 7 and 8. What is this Q here? This Q is the same as the Q we had in Kalman filter. This is the covariance matrix of the transition, or you might call it the process noise. Now, how do we do the correction or the update step? So here, we use those sigma points again. This time, we pass them through the observation function h, which is highly also nonlinear in general, could be, and we get these new data, call them z, and again, using the same wja and wjc, I get the average and the covariance of the z's. I call them z hat and s hat k, where here this rk again is what? The covariance matrix of your measurements noise. Okay? Yeah? So I got z hat and sk. Good. How do I use them? So I pass my sigma points to h. I got the new transform data. I got mean and covariance of them. How do I use them? Let me show you. Before I use them, I need to calculate another thing here called the cross covariance matrix, which is the relation between transform data from F, which we call them xj, and the transform data from H, we call them Z. We want to see if there's x's and z's, which are transform version of the sigma points from F and H, are they showing any cross covariance? So I use my second order weights and calculate this cross covariance matrix between those x's and z's and call it C matrix. And then the same S that I had from the previous step in equation basically 11, I'm gonna use that equation 11 and the C I got from equation 12, I bring them and what? Calculate my Kalman gain, K, which is CXZ times SK inverse. And once the Kalman gain is calculated, then I multiply it by what? By ZK minus Z bar, where ZK are the individual transform Z's, and Z bar is what? From equation 10 and 9, this is the average of them. So this is that innovation term that you have here. Okay, multiplied by that, and then add it to what? Add it to the one that you got in the prediction step. Add it to the average you got from the prediction step, equation 7, right? So this guy comes from equation 7. This guy comes from equation 13. That ZK is coming from 9, and this one is coming from 10. That gives me the updated or the corrected average, and then I use the same K from my equation 13, the S from equation 11, right? And the P that I got from the prediction step, which is equation 8, and that gives me the new updated what? Covariance. Okay, so you see there are lots of equation involved here. That's 4, that's 7, this is 10, right? Just 10 equations, plus of course passing the, well, you already passed them in 9 and this one 6. So there are 10 equations this time for a prediction and correction, and there are what? 5 equations for calculating the sigma points. So you need to use a total of 15 equations for unscented Kalman filter. It's quite a bit complex. And by the way, our data here, our equations and everything, picture, text, equations, not only came from Wikipedia, they also came from what? This great paper, which is called the Unscented Kalman Filter for Nonlinear Estimation by E. Van et al. And this is like the original paper on Unscented Kalman Filter. So this is like the source paper, and I got a bunch of things from this paper here. Okay. Now, is that the only way, these equations 1 to 5, are they the only way to pick up what? To pick up these sigma points? No. Actually, if you look into the literature, there are more than one method for picking up the sigma points, okay? So these equations, they have alternatives. One way is shown here. There are 6 equations here. You see the S0 is the same as before. The W0A and W0C this time are not as simple as last time. Last time they were what? They were simply any equal number between -1 to 1. This time they are picked from some parameters. This method has 3 parameters in it: alpha, beta, and kappa. Okay, it has 3 hyperparameters, and you see that W0A and W0C, the first and second order weights for the first average, they are coming from these formulas. Okay, W0A is alpha squared k minus L over alpha squared k, and W0C is W0A plus 1 minus alpha squared plus beta. So you clearly see these two are not equal anymore. These two entities, they are not equal. And then from S1 to SL, they are coming from adding the previous mean plus alpha square root k times AJ. AJ has the same definition. This is the jth column of what? This is the jth column of A. How did you get A? A times A transpose is that P of K minus 1 given K minus 1, the Cholesky decomposition. So that's the same definition. And then S from L plus 1 to 2L also comes from this bottom formula. You see here, this plus and minus is similar to what you had up here. Look. But these simple constant numbers are now replaced by what? Replaced by kind of more general formulas. So this equation 16 to 21 is like a general version of the original equations. WJAs and JCs are still equal. That's the good part, right? So you see some part of it is the same as before, but some parts are more general. And there is good thing and there is bad thing about it. The good thing is you can, by selecting alpha, kappa, and beta, you can move those sigma points around the average. Here, if you remember, the distance between these sigma points and the average, the side of this equilateral triangle in this simple case, it kind of purely dependent on m or basically square root m. Here, in addition to that, which is going to affect the AJ, you also have some extra parameters to control how close those points are, or what are the sides of this triangle, or in general, the general polygon. Okay? So alpha here determines the spread of the sigma points around the mean. Typically, we pick a very small positive number, and the spread of these points are proportional to alpha. So if you make alpha 2 times bigger, you're going to have twice bigger spread. Okay? Kappa is another secondary scaling parameter, which we typically pick as 0 or very small numbers. And here again says the smaller values correspond to sigma points closer to the mean. And the spread here is proportional to square root of kappa, and you can see that here. Look, here we have square root kappa, but for alpha, we directly have alpha to the power 1. So you see here, and instead of both of them, actually the algorithm could have used one of them. But here they have 2, and then you have the beta parameter here, which incorporates some prior knowledge of the distribution, and the only place it shows itself is right here. And you know WC0 is only going to affect what? Is only going to affect the first predicted P matrix. So if you have any initial knowledge about the distribution, about the sigma 0, then you can add this beta to basically make your sigma 0 bigger or smaller. For Gaussian distributions, the optimal number is 2. And again, this is an over-parameterization because any of alpha, beta, and kappa can be chosen arbitrarily, especially alpha and kappa, which are kind of affecting the same thing. Okay, so this is the reason I mentioned this method. You might say, why did you mention it? This is a little bit harder than that. You have to pick a bunch of things. Is in MATLAB UKF block, this algorithm is used. You have to pick a number for alpha, beta, and kappa. So since I'm going to use that MATLAB block in my demo, I wanted to explain that first for you. Okay, and before I jump into my MATLAB demo, I need to tell you something that clearly, although UKF does not need direct computation of Jacobians, but as you saw, the selection of sigmas, transformation of sigmas, and the update and the correction and the prediction and correction steps, they have way more equations and way more operations to do. So in general, UKF has more computations to do than EKF. Okay, so UKF is basically requiring more computer time and resources. And if you go with this algorithm, you have to have some intuition about how to pick alpha, beta, and kappa. Okay, so now that you know about the overall idea, let's go ahead and talk about the MATLAB code. And now I wrote it for what? Here, you can see the function that I chose and the system that I chose is what we call the Mackey-Glass equations. Now, the Mackey-Glass equations are not something you see in engineering. These are typically a model for what? For blood cell regulations. Why did I pick this one? Because this is the one that you see in the original paper is picked to show the superiority of UKF over EKF. So the type of behavior that you see, first of all, the differential equation is a first order. So this is the state, and this is how the state behaves, and the behavior is chaotic here. I talked about chaos in one of my videos under playlist dynamics. So chaos is extremely sensitive to initial conditions, and in this case, you see it's like a very complicated time series. So if you look at this paper, you see that EKF here does not do a great job, although it kind of predicts the overall trend of the data, but clearly you see that it is missing a bunch of things. Okay, so it cannot really predict the Mackey-Glass time series very well. On the other hand, the UKF, if you look at this bottom one, actually does a relatively good job. So here in this paper, you see that the mean square error for UKF is way less than EKF. And that is because the equations are quite a bit hard to, although they are differentiable, but they are highly nonlinear. Now, what kind of equations are these? Here. The differential equation governing x is dx over dt is a times x of t minus tau. So the hard part about this is the delay. Here, this differential equation has delay in it. And it's also a ratio over 1 plus x of t minus tau to the power r minus b times x. Okay? So the hard part is not just the ratio, it's really the delay that makes this equation what? A little bit chaotic and hard. And in both of these papers, the numbers that are chosen for A, R, B, and tau are these. So A is 0.2, B is 0.1, R is 10. You can show that for a delay of more than 17 or more than 17 seconds, the system becomes what? becomes chaotic. And that is exactly what we did. In this paper, the initial condition is 0.1, in this other one is 1.2. Okay? But clearly, you see that UKF did a way better job compared to EKF. So this is what I implemented in my MATLAB code, so you can see the superiority. Because I tried EKF and UKF on quite bit hard systems like the Van der Pol oscillator or the Duffing oscillator, and in most of these cases, EKF actually did very good, comparable to UKF, if not better. So one of the cases, again, is this Mackey-Glass equations, which are kind of benchmark for seeing how good your system can predict, whether you're using a neural network or a UKF or EKF. So I want to show you what my MATLAB code here. So let's go ahead and look at the MATLAB code, which is a Simulink here. Okay, so this is my Simulink. This is the Mackey-Glass equation, you see. Here, this is negative b times x. This is the delayed version of the function, and if you look at it, the amount of delay is 1700. You might say, well, it was 17, yes, but remember, this is the number of time steps, and the sample time for me is 0.01. So if you multiply this number by this one, that will give you 17 seconds. Because in the paper, that tau is in seconds, but here, this is this many sample times, which is equivalent to what? 17 seconds. So I get this delayed version multiplied by a, then raise it to the power r, add a 1 to it. So here is the numerator, here is the denominator. I get the ratio, I subtract that negative bx. I also add my process noise to it, which here you can see that the Q in this case is 10 to the negative 5, okay? So Q is 10 to the negative 5. This comes out and I add the measurement noise, and R here is 2 times 10 to the negative 5. And then I add them, so this is my noisy signal, which I will pass using a zero order hold, which I explained in my EKF video why I need that. I pass them both to my unscented Kalman filter block and what? Extended Kalman filter block. And these blocks are built into Simulink, so I don't need to make them. You just get these blocks directly. And these guys will give you what? Will give you the x hat, and then we're gonna show the x hat. Now, just like the EKF, UKF also needs two functions. One that is used for the state transition, the other one that is used for what? For the observation. And here, instead of writing them in M files, I use Simulink functions. Remember in my previous video, I said you can use Simulink functions. So here, this is what I did. I use Simulink functions. And one reason for that is because of incorporating the delay. The delay is much easier to incorporate in MATLAB using that Z-1 block rather than to do it in an M file. So directly here, I use MATLAB Simulink functions, and I'm calling those. And you see the initial condition is 1.2. And since I know my initial condition well, the initial covariance, I picked very, very small number. You cannot use 0. This is that Q, this is the R. And the parameters I chose, beta is 2, kappa is very, very small, and alpha is very, very small as well. So I picked these numbers, and I don't have any other measurement or anything. Sample time is 0.1. Everything exactly like that is used in EKF, except EKF does not need alpha, beta, or kappa. So I used all of those. Again, my initial condition is what? 1.2, as you can see. So let's look inside these two functions. The measurement one is very easy. The only thing I'm observing is x. So you see this Simulink function will take the input and just pass it as the output. So y in this case is equal to u, and u here is what you pass to it as x. So this is just an identity function basically. And my state transition matrix is exactly the Mackey equation, except for what? For the integrator. because if you remember, what I need to pass to EKF or UKF is what? The right-hand side. So if I go back here, and if I go look at our EKF, what I need is this guy to pass to it. I need this one to pass to it and this one. But since they are as continuous systems, the thing that I need to pass, this left-hand side, is actually like x dot, right? Equals what? Equals f of x and u. In this case, in this example, there is no u, it's just x. And if you remember, this was what? This was basically equal to, it was equal to this from the paper. So all I need to pass to it for f function is simply what? Is simply this right-hand side. My Simulink should simulate this. And in this case, since my measurement is directly x, so your h function is just 1. Okay, yeah? And that is exactly what I did in these two Simulink functions. The important thing is you name them correctly. So here you see in this F icon that I have up here, you have to double click and what? Pass the function name to it. Just adding it as a name under this is not enough. You have to pass that name to it so MATLAB can call it. So here I pass my actual x as well as the UKF estimate of x and EKF estimate of x to here. And here I also show their errors by subtracting actual x from what? From these estimates. So if I go ahead and run it, which I did here, and you have to run it for quite a bit time, definitely way more than 17 seconds, which is your delay. So here I ran it for 300 seconds, and you can see the results here. So if you look, the blue is the actual signal, and the green is UKF, and the red is EKF. And you can see that UKF is doing way better job than what? Than EKF does. You might say, what are these kind of like drops or dripping or this kind of sudden behaviors? These are just because of those delay that we have in the system. These are the effects of delay. So these are kind of like an outlier that you can ignore. But clearly you can see that UKF is doing way better of a job than what? EKF. And if you look at the error also, you can see that EKF error is way higher than what? Than UKF. Okay, so you see that my unscented Kalman filter is doing better job than extended Kalman filter. So hopefully this relatively long video was useful to you. You learned some basics behind the scene about the UKF. And I showed you some good papers and some good resources. So hopefully you can learn more from this video. Thank you so much for your attention. I'll see you in the next lecture.